Hi children, how are you? Hope you are fine and safe. Today we are starting our new chapter, that is the 13th chapter, namely magnetic effects of electric current. First I will give you an introduction to this chapter. That is, here I am starting by drawing a electric circuit. Okay, in the previous chapter we studied how to draw an electric circuit. That is, the battery is here and a key is here, and I am connecting a resistor. Yes, okay, here the resistor is here and the key is here, and I am switch on the key here. I am switch on the key. Then what will happen? The electric current will flow through this key. That is, the electric current will flow from here is the positive end of the battery and here is the negative end of the battery, and the electric current will flow from positive to negative. These are all we discussed in the previous chapter. Okay, here I current will flow through this. Okay, this electric circuit is a current carrying electric circuit. Okay, or otherwise this electric circuit can be called as electric current carrying conductor. Conductor means anything that conducts electricity is called conductor. Here this is also a conductor, so we can call it as electric current carrying conductor. Electric current carrying conductor. Okay, anything that conducts electric current, that means the electric current carrying conductor. Here this is electric current carrying conductor because here it passes the current. And the first point of this chapter is, and this point is very important, and this chapter is based on this point. Okay, that is, this electric current carrying conductor behaves like a magnet. Have you heard about magnet? Okay, in the toys, I think in the 7th or 8th standard you studied about the magnet. Magnet has two poles, that is north pole and south pole. Okay, there is two poles for magnet. This is a bar magnet, north pole and south pole. This is a magnet. The magnets attract and repel. The magnet has a property of attraction and repulsion, that is, like poles attract each other and unlike poles repel. That when I give another magnet near to this, when it has the north pole repel, south pole repel. That means like poles repel and unlike poles, that means the north pole and south pole will attract. Okay, these are all you studied in the previous classes. Okay, electric current carrying conductor behaves like a magnet. Behaves like a magnet. How is it possible? That is, this electric current carrying conductor behaves like a magnet. Heard about magnetic compass? We all use this magnetic compass for finding the direction. When we travel through unknown places, we use this magnetic compass to know the direction, that is, whether it is north or south or west or east. Here you can see a compass needle and a current carrying conductor. Okay, let's do an activity by using these two. Are you ready? Here when the current flows through this electric circuit. Suppose the current flows through this electric circuit, what will happen? If you keep a compass needle near the current carrying conductor, what happens? You can see in the picture. Yes, the compass needle deflects. If you keep a compass needle near the current carrying conductor, the compass needle deflects. When current passes through this wire and we place that compass near that wire, the needle deflects. Now we know the fact that if we keep the compass near the magnet, the needle in the compass show deflection. You can see it. When the compass placed near the magnet, the needle shows the deflection. At the same time, when the compass needle placed near the current carrying conductor, it deflects. The compass needle deflects. Do you know what is the reason? When current flows through the wire, it becomes a magnet. The electric circuit becomes a magnet. This is the reason that compass needle deflects when brought near the wire, or the compass needle deflects when brought near the electric circuit. Then we move on to our first topic, that is magnetic field and field lines. What do you mean by magnetic field? There is a magnet, that is North Pole and South Pole. I take a iron piece and put near to the magnet. It does not attract or repel. When I put this iron piece near to this, it feels a force of attraction. Okay, then I take it into here and we feel more attractive force here, and it get attracted to the North Pole. At some distance it does not feel any force of attraction. That means this magnet has a place. Suppose this is the region in which the magnet gets attracted the iron piece. Okay, when I put the iron nail anywhere of this place, the magnet attracts this iron piece. When I place the iron piece anywhere in this region, in this place, the magnet gets attracted the iron piece. But when I place the iron piece outside of this place, of this region, the magnet does not attract. That is, here the force of attraction or repulsion of this magnet is concentrated at this region. Okay, at this region. That means, and that region, the force of magnet, that is the force of magnet is concentrated at this region. Outside this region, there is no magnetic force. The force of magnet is not experienced. That means we can understand that there is a region in which the force of magnet is experienced, and that region is called magnetic field. Magnetic field. So every magnet has its own magnetic field. And what is magnetic field? The region surrounding a magnet in which the force of magnet can be detected or experienced. The force of magnet can be experienced. Hope you understand what is magnetic field. And this magnetic field, the term magnetic field is a vector quantity. That means this magnetic field has both direction and magnitude. What is magnetic field? That is the region surrounding a magnet in which the force of magnet is experienced is called magnetic field. And the next one is the magnetic field lines. What do you mean by magnetic field lines? That is, this magnetic field can be represented by the magnetic field lines. How can we represent the magnetic field lines? Then, what is magnetic field lines? This magnetic field can be represented by using these magnetic field lines. Here, this is the magnetic field lines of the bar magnet. Here is the north pole and here is the south pole. Okay. When I place an iron piece here, it does not attract to this. It does not experience any force of magnet. And when I place this iron piece here, it will experience a force of magnet. It will experience the force of magnet. Okay, because it is inside the magnetic field or it is under the magnetic field. So, this magnetic field represented by the magnetic field lines. Then, what are the properties of magnetic field lines? Then we can move to the properties of magnetic field lines. Here you can see from this figure itself, you can say the properties of magnetic field lines one by one. That is, the first point is the direction of magnetic field lines. I already told you the magnetic field has a direction. That is, the magnetic field is a vector quantity. So, magnetic field has a direction. And what is the direction of magnetic field here? Here you can see the magnetic field lines is starting from the north pole and it reaches at the south pole. Here these magnetic field lines all are starting from the north pole and comes to the south pole. Okay, so the direction of magnetic field is outside the magnet. From outside the magnet, it is from north pole to south pole, and the magnetic field lines is a closed curves. Here also the magnetic field lines passes not only through the outside of the magnetic field lines passes through the inside of the magnet also. These magnetic field lines passes inside of this magnet. Okay, here the magnetic field lines is a closed curve. Okay, first point is the magnetic field lines is a closed curve. That is, outside the magnet, the magnetic field lines passes from north pole to south pole, and inside the magnet, the magnetic field lines passes from south pole to north pole. Okay, inside the magnet, it passes from south pole to north pole. Okay, so magnetic field lines is a closed curve. This is the first point, and the second point is this outside the magnet, the magnetic field lines moves from north to south pole, and inside the magnet, the magnetic field lines passes from south to north pole. Okay, hope you understand this. Then, how can we identify the strength of magnetic field by using these magnetic field lines? Okay, when I place the iron piece here and here, it feels more force of attraction when I place the iron piece near the bar magnet. When I place the iron piece near the bar magnet, it feels more force of magnet. But when I place here or far from the magnet, it feels only less force of attraction. Here we take a part here. I take a part here and at the poles. At the same, on looking at these two places, here only two magnetic field lines is passing, but here at the poles the magnetic field lines is, the number of magnetic field lines is very more, so it has very strong magnetic field. It has only very weak magnetic field. Okay, here the magnetic field is very weak and here the magnetic field is very strong. So how can we determine the strength of the magnetic field? That is by the number of magnetic field lines. Otherwise we can say that if the magnetic field lines are close each other, here the magnetic field lines are close each other and here the magnetic field lines are far each other. Okay, so when magnetic field lines are close each other, then the magnetic field will be very strong. Okay, when magnetic field lines is very far apart, then the magnetic field will be very weak. Then there is another point, that is the number of magnetic field lines per unit area is the measure of strength of magnetic field. That is we already discussed. Then the two magnetic field lines never intersect each other. Here the two magnetic field lines never intersect each other. If they intersect each other, suppose if these two magnetic field lines intersect each other, here we can find the direction. The direction is the tangent of these field lines. Okay? And when it intersect each other, it has two, these magnetic field has two tangents. At the same point, it has two direction. Here it comes two direction at the same point when the magnetic field lines intersect each other. So it is not possible. So the magnetic field lines never intersect each other. When it intersect each other or when it crosses each other, it may have two direction because the direction is the tangent. At the same point it happens two direction. It is not possible. Hope you understand. These are all about magnetic field and magnetic field lines. Here we discussed mainly the 2 points, that is magnetic field and magnetic field lines. The region surrounding a magnet in which the force of magnet can be experienced is called magnetic field, and this magnetic field is a vector quantity. And we are also discussed about the magnetic field lines. The magnetic field lines are closed curves and continuous curves. Closed and continuous curves. It does not end. And outside the magnet, the direction of magnetic field lines is from north pole to south pole. Inside the magnet, the direction of magnetic field lines is from south pole to north pole. The strength of magnetic field can be determined by the number of magnetic field lines. Magnetic field lines are close each other, then there will be strong magnetic field. If the magnetic field lines are far apart, then the magnetic field is very weak. Okay, the two magnetic field never intersect each other. Never intersect each other. If the lines intersect, at the point of intersection, at the point of crossing, there will be two direction. It will not be possible. There will be two direction for the same magnetic field. It does not possible. Any quantity has only one direction. It does not possible for one quantity two direction. So these are all about magnetic field and magnetic field lines. Then we will continue in the next class with a new topic, that is magnetic field due to a current carrying conductor. Then we will continue in the next class. Thank you.